Everyone, well, in this lecture, we will examine the second approach for deriving the Takagi-Sugeno models, well, not only the Takagi-Sugeno, but in general, we will start from the simplest structure, which is represented by singleton model, and then we will see the, well, in theory, is the most complete way for modeling a nonlinear dynamic process, which is represented, as I said before, by a Takagi-Sugeno. And in this lecture, in this module, we will see the second approach that uses the data-driven construction. So it means that we are using the data from the process, and they will be used for estimating the parameters of this prototype. So the structure, let's talk about the structure and the parameters. So the structure in general is driven by the input and the output variables. And for dynamic systems, we will see in the application part of this course. Of course, we need to introduce the representation of the dynamics of a process. And the structure depends on the number of membership functions, which is defined one per variable, the type of membership functions, and also another important point is represented by the number of rules that will be used for approximating our process. While the parameters are represented by the parameters of the consequent variables, and they will be used, they will be derived using the least square, or a very simple least square approach. And regarding the antecedent membership functions, there are several methods, and we will see one of the most powerful approaches for deriving the membership functions. So let's start with the simplest approach, which is represented by the estimation of singleton, of models in the singleton form. So we have the single rule Ri, which is called I means the generic rule. If X, so the input, belongs to the fuzzy set AI, then the output corresponds to a singleton. So given the fuzzy sets AI and a set of input-output data, so normally they are represented as well, in the static case, as a vector of the independent variables xk and the dependent variables. Well, we are assuming that we are considering single output processes, because is simpler to manage this case, and k is the number of data. So we are considering a number of data equal to capital N, and we will see how to estimate the optimal parameters. So once we have computed the membership degrees, mu AI, depending on the variable, on the input variable x key, so we can normalize this parameter, which is represented by gamma ki. So I depends on the number of fuzzy sets or fuzzy rule, which is the single membership function divided by the total number of membership functions. Remember, if we have a global coverage, this summation is 1. So it means that the gamma is equal to the single membership function. So the output is represented as a summation of all these terms gamma ki and multiplied by bi, and it can be rewritten in as a is in a matrix form if you collect all the outputs, independent outputs, and a matrix gamma and a vector B. So you have y equal to gamma is a square matrix and or a rectangular matrix, and the vector of the unknowns B. So B, using a least square estimate, can be computed as a inverse of this multiplication of the transpose of gamma multiplied by capital gamma. So inverse multiply the gamma transpose by y. So y is the known term and B is the unknown term. Note that normally, depending on the data, this matrix is assumed to be non-singular. So it means that the matrix gamma has a full rank, or the number of independent columns is maximum. So you have this estimate of the unknown variables. So the least square estimation can be rewritten in this form. So you have the matrix which contains all the input variables depending on the data, and refer to the single cluster or rule, and the vector of the outputs to the dependent variables y and gamma. So gamma contains is a diagonal matrix which refers to the single rule or the single relation, and is described as this form. So once you consider the consequence in not in the as a singleton, but as a linear, with a linear relation that we'll see later. So you have to estimate not only the parameters B as for the case of the singleton, but also the which is represents like a bias. But you need to estimate also the parameters that link the independent variable x with the output, the dependent variable y. So there are two approaches. The first one is called global least square, because if you notice, the global parameter vector, which is the theta is the it contains all the single vector theta, each one for each cluster, is in this case. So C is the number of clusters. We will see later the concept of cluster or the rule, the ith rule we saw in the previous slide here. Is here, or so for the case of the global least square, you can see here that you have a minimization of the least square cost function, which is represented by this matrix, which is a collection of all the xe, if you remember, contains x plus 1, because 1 is the vector which multiplies the constant variable bi, and so you have one gamma matrix, one for each rule, and then it means that the global least square is optimizing in the least square way all the parameters in all the rules with respect to all rules. There is another approach which is called local least square. In fact, for the case of the local least square is a little bit different, because you are optimizing for each so you have the same capital X E but you have gamma e. So you are, for each rule, you are estimating the local parameter vector. So it's why it's called local. So the difference between the local and the global is that in the local, each vector optimizes the local model in each rule. In the global, so the global model is optimizing in a global, in an overall sense, your data, your parameters. How we can, so the second, once you have optimized or estimated the parameters, so you have to estimate, to recover or derive the membership functions. So there are several ways available in the literature, and for example, you can perform a grid partitioning. So in assuming a specific form of your for your membership function, you perform by using a trial and error procedure, partitioning into a grid of different membership function. You can perform, as we will see in the toolbox that we will use in our practical process. There is a nonlinear optimization, which is represented by a neurofuzzy method. A construction, a tree construction is another way that allow you to estimate the membership functions. And the way we are using here, and it is used for introducing the problem of the nonlinear optimization, is called product space fuzzy clustering. So which is the idea of the fuzzy clustering of the data? So let's assume to have two clusters, as in this case. So what is the concept of a cluster? Cluster is, in general, is a set of points that have similar characteristics, the points that belongs as in this example. So you have a set of data here that have similar characteristics, and each point of this cluster has similar characteristic to each point of belonging to the same cluster, but is different, so is quite dissimilar. So remember also the concept of similarity, or better, dissimilarity, when we introduced the fuzzy logic. So you see here that the points in this cluster are similar one to each other with respect to the other points of the other cluster that are quite dissimilar to this one. So in order to derive the form in a mathematical way of the cluster, you need to introduce the concept of cluster center. So what is a cluster center? Well, a center of a cluster can be interpreted as, for example, here, the center of gravity. You can see here that it is quite close to like a medium. You perform a median or a mean value of all your coordinates, and you find the center of gravity of your points, and the same for the case of V1 or V2. So you have a vector of your cluster centers, they are called means, and so this vector contains the centers of your cluster. They are also called prototypes. And then if you check the distance, we will see later the concept of distance, but distance is represented by these arrows, and D, you can see that D is computed with respect to, is computed for the point, the generic point Z key, with respect to the center that in case is V1. And you can see here that you can perform this computation of the distance for each point of this cluster with respect to this center, but you can perform the computation of the same distance of the points of the second, which are nearer to the second cluster, to the second center of the cluster, with respect to the first point. So you can, for each point, for each center, you can perform, you can compute a number of capital N distances. And the same for the distance of each point from the second cluster. And then so you perform for each cluster, for each center, you can perform, you can compute this distance. So you have, in this case, you have the distance of the point Z key with respect to the center eta or mu or VE and V2. And in this way, if you can perform, you can see here that depending on these membership functions, so in principle, you can link this distance, as we will see later, to the concept of membership function, if you remember, which represented the degree of how much a point belongs to a fuzzy set, if you remember the concept of the partition matrix. So you have for each, you can see here, for each cluster, you have a set of fuzzy of these points. These are numbers because you have for each point, in fact, you have a number of column n, so a number of column which is equal to the number of data, and a number of rows that is equal to the number of centers. And you have this fuzzy partition matrix. And then you can also estimate the shape. You can see here that for the case of the cluster or the fuzzy set, you can see here that it is almost circular, but for the case of the second cluster is closer to like an ellipsoid, so it's slightly different from a circular shape. So how we can solve this fuzzy clustering problem, as in, of course, is just to sketch you the problem, but of course we are not going to solve it directly, but it is solved automatically by the fuzzy, by the toolbox provided by MathWorks. So given the data, you can see here that you have a number of data, the key, and key is the number of data n. You can find the fuzzy partition matrix, and you can see here that you assume that you have, as we said earlier, we have one column for each data and one row for each cluster, and we have a vector of the cluster centers. And of course, V can belong to an n-dimensional space, as here for the case of the data can belong to an n-dimensional set. So the fuzzy clustering is recasted into an optimization approach. So it means that you are using a criterion which is very close to the least square concept. So you obtain these objectives, this cost function, which is represented. Of course, it depends on the number, the data Z, and is defined by the fuzzy centers V vector, the matrix of the fuzzy memberships, fuzzy membership functions, and the fuzzy sets AI. And of course, you can see here that this summation is performed over these distances that we will see later. The form, of course, the distance, as you remember, depends on the point with respect to the center and is defined with respect to a possible norm, we will see later. And then you can see that for each point, for each cluster, you have a membership function, and also you have a power m. Well, m is a number, or is a real number, is a positive, and can in a range, is normally in the range between 1 and 2, maybe a little bit greater than 2. And it represents the way how the membership function decreases with respect to the input. So the higher, the larger is the m, the higher the decreasing of this function is. So it represents in some sense the degree of the intersection between the clusters. And of course, the minimization of this cost function is subject to these constraints. This one is, of course, something that you know, because the membership degrees, the membership degree varies between 0 and 1. And we have also this condition that you can see here for each cluster, this summation, so the sum of all the membership degrees for each cluster needs to be greater than 0 and less than n. So it means that we don't have any cluster empty, because if we have a cluster empty, it means that we don't really need this cluster. And then the other concept, the summation of all the clusters, of all the membership function with respect to the cluster for each is something is quite similar to this condition. So is equal to 1. So it is, if you remember, is the concept of the total membership. So this algorithm is performed as a recursive procedure, as a recursive algorithm. So normally you have this loop. So you have a starting point. You you compute the centers of the clusters of your prototypes with this formula. So it's something that is computed as a starting point, and then for each point you calculate the distances. So for each center of the cluster and for each point, so you have a matrix of all these values. And then you update the partition matrix, and you can see here how the partition, so which represent in a discrete way your membership function. So it represents, as you can see here, the distance, so a summation of the with respect to all the cluster, the distance of the point I with respect to the cluster I of the point T, with respect divided by the distance of the point J with respect to the centers, the distance with respect to the centers J of all the clusters of the same point. So you are performing, if you remember, this computation for all the clusters in all the distances, and you obtain this value until you have a stabilization of the variation of your matrix U, which contains, if you remember, these vectors. which kind of of distance measures we can consider? Normally, we consider the Euclidean norm, which is normally, as you can see here, is the difference between the distance of the points with respect to the center. You can consider an inner product norm because the same distance is normalized with respect. So it has a weight, is a weight. You are weighting the distances, or there are some other possibilities that we are not considering here. So for the case of the fuzzy C-means, because it's called fuzzy C-means because it's considering a number of clusters and is performing a computation of the centers of the cluster. This is an example of an extraction of the rules by fuzzy clustering. So we have this data in order to have an example that can be represented in a two-dimensional space. So we can an independent variable x, the dependent variable y, as this form. So you can see here that this model, which is of course is a static model, can be represented in as you we can see depending on the degree of accuracy you want to reach. But in principle, you can see that it can be described as, for example, as a linear model here. Then we have a second linear model here, then a third local linear model here, and then a fourth model. So perhaps we can assume, as in this picture, that we can assume that 4 clusters hold for describing your model, and then in order, if you remember the concept of the projection, so you can assume that each cluster is projected into one space for the case, for example, of the input space, and you can assume in principle this form for your fuzzy set for the input x. And in this way, you have a number of 4 clusters, and you have 4 rules for describing your model. So in each set, so if you read here the description as a in a rule-based form, so when x is in the fuzzy set AI, the cluster 1 is ruling. When x is equal to A2, the second cluster, the second rule is fired, is ruled, and so on. So for each cluster, you can use a local linear description of your model, which represents the advantage of the use of a fuzzy model. Of course, you can think of projecting your cluster onto the the second space of y, and you obtain what is called, well, it's not really used, but it's called the inverse Takagi-Sugeno model, because it's describing the output as a function of the input. And we will see a demo, later, how we can extract the Takagi-Sugeno rules, especially for the use of the fuzzy control. So in the next module, we will see how we can use this concept, the concept of the principle of the derivation of these models that are used for designing in an automatic way the controller, because the advantage of a fuzzy logic is that, and the fuzzy model is that you can estimate, you can derive your controller by using the input-output data. Okay, thanks for your attention. So the next module in the next module we will see how we can derive a fuzzy controller. Thank you for your attention.